Oh, it's frozen. Frozen. Awesome. So basic buffers. Basic buffers, same thing really holds, except that because they're buffers, they're basic, they're a weak base with their own conjugate acid present. pHs of these are going to tend to be on the high side rather than on the low side. Okay? But the same general principles of everything that we've talked about applies in this situation. You have an equilibrium. In this case, this is the ammonia buffer, a specific example. Okay? But you have an equilibrium, so you have all four of those components in there at the same time. Now, also caution, right, it's a hydroxide that's part of this equilibrium. So it's also a Kb and a pKb and a hydroxide, so you're not going to be getting a pH directly out of this. The Henderson-Hasselbalch equation doesn't work exactly the same way here because this is a base, and Henderson-Hasselbalch is based on an acid, so it's a pKa plus. Now you can modify the Henderson-Hasselbalch to still be able to utilize it. But just realize that it's not quite the same situation. So typical Henderson-Hasselbalch written in terms of a weak acid. So how would we write this Henderson-Hasselbalch in terms of a weak base instead? If you look at the equilibrium of the conjugate acid, the acid component of this entire equilibrium, then you get this equilibrium, and this equilibrium has a hydronium in it. Awesome. And this equilibrium is not the same as that one. This one is a Kb, right? Kb. But what I've written down here, where I put the conjugate acid on one side and the conjugate base on the other side and turn it into an acid-type reaction, now I've got a Ka. So, one way to solve this problem, and still use the Henderson-Hasselbalch equation, is to recognize that there's a relationship between Ka and Kb. So if I know the pKa, if I know the pKb, then I can determine what the pKa is, plug it into my standard Henderson-Hasselbalch equation, and still do my calculation, and still function. It is still, that logarithm is something over something, so that logarithm is still the base form over the acid form. So it's still the same type of formula. So don't let the fact that the other one was A minus and HA, it's still A minus is the base form, HA is the acid form. And this one is B and HB on the bottom. Still the same kind of format. So to me, this is the simpler way, my typical method. Fortunately, we don't have to use basic buffers very often. But when you do, to me, this is the simpler path for their analysis. Is don't just follow the standard base that you stuck with. Switch it into the acid side, and then go right back to your Henderson-Hasselbalch and do your calculation. So of course we know pKa, pKb, you add the two up and you get 14, so if the pKa is 3.15, then you know the pKb is 10.85. Okay? If you know the pKb is 12.2, then you know the pKa is 20. So off we go. That's kind of thing. I will work through this relatively quickly, expecting that you can work these out. And again, the only twist here is the fact that, yes, this is a base. So it's a weak base and it's conjugate acid. And you're going to be given either a Kb or a pKb because it's a base. But all you do is take that K change it from B to A. Get it from a base to an acid. That's what we need to do. So it's 0.50 molar in ammonia and it's 0.20 molar in ammonium chloride. The ammonia, that's the base side of that, and the ammonium of the ammonium chloride, that's the conjugate acid. So all that stuff we did about picking out acids and conjugate bases and bases and conjugate acids from a couple of chapters back, that's what we did. So if I want to know the pKa, all I got to do is subtract that off of 14 and I have the pKa. So the pKa for this equilibrium is 9.25. So the pH is going to be 9.25 plus the log of the base on top and acid on bottom. And which one of those two numbers goes to the base? 0.5. That's the base. So having decided that, the 0.2 must be the acid part. Okay. So this pH calculation is relatively quick and simple. The log of 2.5 is something. pKb is 4.75. Ka is 10 to the minus 9. The concentration of the acid is 10 to the minus 1. Mucho good. If you like the base equation, and you want to use the base equation, there is actually a form of the Henderson-Hasselbalch in terms of hydroxide. I personally don't use it, but you're welcome to use it. The only reason I don't use it is because notice what's next to that logarithm. Notice the acid form over the base form. I don't use it. So I can just keep track of one direction and go. But it's up to you. It's up to you. As soon as I say POH, then it reminds me that that needs to be pKb. And then if I remember that acids and bases are opposites of each other, then I'll remember to change that log to the acid over the base. But still, this doesn't give me pH, right? It gives me POH, so I got to do one more step to get from POH to pH, because we're always focused on pH. So for me personally, I would rather put that extra step back on this previous example that we just worked. I would rather do my extra step right here where I get from pKb to pKa. That's just whatever works for you is what you want to do. Just like if you like an ice diagram, you're welcome to use it. And I have had students before, by the way, who don't like the X is small approximation, and they will always use the quadratic. It's not what I would do. Okay. Yes, it's more precise to always use the quadratic analysis on an ice diagram, but the additional effort most of the time is not significant enough to make a difference. So it doesn't seem to have a purpose for me. But it's up to you guys. So for me, I like this one. Just use my standard Henderson-Hasselbalch. pH is pKa plus the log of base over acid. And just if I'm working with a basic equilibrium, let's just push it over and use the pKa of of it instead of the PKB of it. But I can do that. As soon as I know what the PKB is, I just subtract it off of 14 and I got the PKB. But if you want the base form, there it is, the base form. I'd rather keep track of one calculation or one equation rather than two. So I'm not going to specifically work that example. So here's what I do want to move on to. So buffers. They resist changes in pH. They consist of typically a weak acid and its own constant base. But it can also, as we just saw, consist of a weak base, a weak base and its own conjugated acid. Okay? So that'll work as long as you've got those two components, because when you add acid, it reacts with one part of it. When you add base, it reacts with the other part of it. That's how they do what they do to resist changes. The other side of a buffer is something called capacity and range. Okay. If you add hydroxide to a buffer, the pH goes up, but not by much. We did that calculation. It went from 4.75 to 4.83 for that acid-base buffer. So we only added 0.01 moles of sodium hydroxide. We can add another 0.01 moles of sodium hydroxide. We'll get some new numbers, and the pH will go up a little bit more. We add another 0.01 mole of sodium hydroxide, and you do some calculation, and the pH will go up a little bit more. But if you remember, every time you add the hydroxide, it was reacting with the acid form of that buffer system and changing it into the base form of that buffer system. Right? That's what the base was doing. If you add hydroxide, it's going to react with the acetic acid, it's an acetic acid buffer. Hydrofluoric acid, hydrofluoric acid buffer. It's going to react with the acid formula, reduce the amount of the acid formula. But eventually, you're going to add enough base that you will have removed all the acid. But every time you add base, you take away a little bit of acid, a little bit of acid, a little bit of acid. Eventually, you'll get to the spot where that you've taken away all the acid, and boom, you no longer have the buffer. And then the pH starts going quickly up. Almost to zero. Not quite, but almost to zero. You had pure water. That's not a buffer at all. What you've done there is you have exceeded the capacity of that buffer. There's a limit to how much acid or how much base that buffer can neutralize. So those graphs you were doing the other day, there was a slight increase and all of a sudden it jumped. And you're adding hydroxide. You had a buffer right in here for 2, 3, 4 drops. But then you hit neutrality, which means you had consumed all of the acid form of that buffer. And it's gone. And the pH shot up. As you add this acid and base, eventually you can exceed the capacity. So that's one side of the buffer. A buffer has a capacity. The other side is the range. So the pH starts at 4.75 for that acetic acid buffer, and it goes up to 4.83, and then it goes up, and then it goes up, and eventually one drop makes a huge change, rather than just a small incremental change. So what's the pH right when that big jump starts to happen? Well, that's the upper limit of the pH range. If you were adding acid, the pH would be going down instead of up. So again, eventually you would add enough acid to consume all of the conjugate base in the buffer, and then the pH would drop quickly. So what's the low pH to the high pH? What's the range of the buffering capacity? How high of a pH does it get before it makes a quick, in other words, no longer resists? Or how low can it get? So there's a pH range and there's a capacity. pKa is 5. Henderson-Hasselbalch pH is equal to pKa plus the log of A minus over HA. The equilibrium is the HA plus hydroxide into A plus a couple of things. That's stoichiometry reaction bit. If I have a 0.1 mole, pH is 5. 0.18, 0.02 mole, the pH is 4.05. What's the difference between those two? The difference between those two is the one on the right has a much larger ratio of acid to base. The one on the left has equal amounts of acid and base. So this pH starts at 5, that pH starts at 4. But what you should notice is there's not a whole lot of this conjugate base available. So this buffer on the right is not going to have much capacity against any acid, against any acid that comes in there. Because a little bit of acid is going to strip that conjugate base entirely because of its small amount. We run some numbers. You can run these numbers yourself, so I'm going to move through these numbers relatively quickly. Might be good practice for you to go back and do these calculations yourself. But on the buffer on the left, if I come in here and I put 0.01 moles, this is the one we did earlier. 0.01 moles, it's not the same one. 0.01 moles. And I run a calculation, the pH goes from 5 to 5.09. Not much of a change. If I do the same thing to the buffer on the right, 0.01 moles of hydroxide, and I run the numbers, and the pH goes to 4.25. So the one on the left, the pH changes by 0.09 units. The one on the right, the pH changes by 0.2 units. And neither one of those sound like large numbers, not here. But in fact, the buffer on the right, pH has more than doubled. The change is more than twice what it is on the left. And remember that pH changes are logarithmic. So even though we doubled more than doubled the actual change, that doubling is even more significant because it's a tenfold change for each one. So although the pH change has doubled, the actual hydronium concentration is more significant. But still, we've got a difference, a greater difference. Get this out of your way, but 2% change for the one on the left, 5% change for the one on the right. The conclusion I draw from that is up there in the blue print. The conclusion that I draw from this is you will be most effective if you have as close as possible equal amounts of conjugate acid and base. Acid and conjugate base, however you want to say that. Equal amounts is your most effective buffer. So that's your most effective buffer. The further you get from equal amounts, the less effective your buffer will be. So most effective with equal concentrations of the acid and its conjugate. Let's look at these two buffers. These are both equal amounts. The one on the left is a 0.5 mole, 0.5 mole. Of course, the initial pH is going to be whatever the pKa is. In this case, it has to be 5. The buffer on the right is equal amounts, but it's 0.05 versus 0.05. So they're both going to start at a pH 5. Now let's run an analysis on them. Let's add 0.01 moles of hydroxide to the one on the left. Run the numbers, and you end up with a pH of 5.02. So the pH goes up, of course, you added hydroxide. But it goes from 5.00 to to 5.02. Not much. Well, let's do the same thing to the buffer on the right. Let's add 0.01 moles of hydroxide. And see what happens to the pH there. It goes from 5.00 to 5.18. I see a difference in those two. So for the buffer one on the left, my pH went up by 0.02. For the buffer on the right, the pH went up by 0.18. That's almost 10 times. Less than 0.5% change on the left, and almost a 4% change on the right. Significant difference. So what do I learn from that? Compare blueprint. The most effective buffer is one who has a high concentration, higher concentration. Now in practice, eventually you run into the thing, well, why not just make the highest concentration always? In practice, there's sometimes a limit, like solubility comes into play. So sometimes there's a limit to how high that concentration can be. And sometimes other chemistry starts to happen. Remember those drugs that you're doing in a buffered solution? Sometimes your chemical that you're testing will actually react with the buffer component. That's not good. That's not what I want my chemical to react with. I've got another reaction I'm trying to test, but then my buffer components are going to interfere with that. So I've got two options. One is, the one I picked, is find different buffer components that give you the same pH. That's hard. That's hard to do. Remember, I have no control over what that pH is going to be initially. If I use equal amounts, the pH is simply a product of the Ka. If I use equal amounts, the pH is going to be the pKa of that acid. I was done. So if I choose a different substance, it's going to have a different K and a different pH. So I may not be able to use it. So what are my other options? My other option is to use a little bit of dilute buffer. Maybe reduce the amount of reaction. But again, when I start diluting my buffer, I lose capacity. Okay? So it's always this trade-off kind of thing. It's the way things happen. Okay? So buffering capacity. Concentrated buffer, dilute buffer. Concentrated buffer, you got obviously more ability to neutralize. Again, for every mole of the base that goes in there, it's going to switch over a mole of one of those. Okay? For every mole of acid that goes in there, it's going to switch over a mole of something. So, the more concentrated the buffer, the more ability you're going to have, the greater the capacity. So, bottom line is this. Because of those two things, capacity and range, your most effective buffers, is going to be equal amounts, 1 to 1. Now, as long as you don't get more than 10 to 1 ratio, you can still keep a reasonably effective buffer. What that means is, remember that 10 to 1, 10 is a pH 2 range. 10 to 0.1, sorry, is a pH 2 range. So up 1 or down 1 from whatever that pKa is. So if you're trying to make a buffer, you look up the Ka and you find one whose Ka is either 1 above or below whatever your target is. Ideally, you want one whose Ka is what your target is. So if I want a pH 7.4 buffer, and I can't use the carbonic acid carbon dioxide because it's too difficult to work with, I need to go find some other weak acid whose Ka is close, pKa is close to that 7.4. I can work with something that's a little bit below that or a little bit above that, as long as I stay within my range of up or down 1 from its pKa. And of course, the buffer will be most effective when the actual concentrations are high. So 0.5 molar equal makes a much better buffer than 0.05 molar. So there's just some math here, but this is basically what I just said. The effective range of a buffer is plus or minus 1 pKa. Whatever the pKa is, up 1 or down 1, that's your effective range for a pH. That's your effective pH range on a buffer. So, when you want to make a buffer and your conditions require you to use a 10.2, I don't know where you're at or what's going on, but for some reason you need a buffer that has a pH 10.2. And what you need to do is find an acid that pKa is as close to 10.2 as you can get. Definitely between 9.2 and 11.2. Those are your options. Because the buffer's pKa up or down 1, that's what you want. So you want to find someone whose pKa is closest to the pH of your buffer. That's what you want. Practical thing here. The other day in lab, acid-base equilibrium, I had these 12 bottles of buffers that need 1, 2, 3, 4. You know where those come from? They come by choosing a weak acid. Okay? Whose pKa is close to 4, and then I make even amounts, and I get a pH 4 buffer. And then to get the pH 3 buffer, I can use that same one, but push it to its limit, make a pH 3 buffer, and then push it the other way and make a pH 5 buffer. But then how do I get a pH 6 buffer? I got to choose a different acid-base system. And maybe make a 6 and 7 and 8 out of that. And then maybe make a 9 and 11, but then somehow we're going to get a 12, and somehow I'm going to get a 1 or 2. So that's what you have to do. When you make a series of buffers, you've got to go back to the acids and figure that out. So you got to figure pKa closest to whatever buffer you're trying to make. So, practical thing right here, let's make a choice. Which of the following acids would be the best choice if I want a pH 4.25 buffer? Which one would be the best choice? There's 3 of them there: chlorous acid, nitrous acid, formic acid, hypochlorous acid. Something that's formatted in on hypochlorous acid, don't take that as an engineer, that's so which one do you want to use? That would be my choice, formic acid. It's not 4.25, but out of those 4 choices, it's the closest one. Where did I even get those 4 choices? Maybe I went to my shelf, and that's what I had on the shelf at the stock room. I said, okay, I've got these 3 acids, and I've got all of their conjugate base salts. Or I can get their salts. That's another option, is to make the salt yourself. Would any of these others be at least acceptable? Formic's the best. Could I use the chlorous acid to get a pH 4.25 buffer? Probably not. 4.25 means I can go down to 3.25. Or I can go up to 5.25. So how about nitrous acid? I could probably get away with that. Again, I'm kind of near the edge of its range. But I could probably get myself above it. It wouldn't be quite as high capacity because of the ratio of acid to base I have. And hypochlorous acid? No, that one's too far away. Overweight. 7.54. What kind of a buffer could I maybe use hypochlorous acid for? They keep talking about overweight, right? What? pH what? Yeah. Maybe I could use hypochlorous to simulate the blood pH, right? The 7.54, that's pretty close to 7.4. Maybe. Unless, of course, some reason the hypochlorite ion reacts with my drug I'm trying to test. And actually, hypochlorous acid is one of the components that's in bleach. So maybe that's okay, and maybe that's not right. Alright. So, now that we have chosen, let's do the next step. If I want a pH 4.255, and I went to my stock room and I got all these, and out of all those, I want to choose formic acid. The next logical question to ask is what ratio of formic acid to formate ion, right? Because that's what my butter is made out of. What ratio of acid to base do I need to use in order to get that pH 4.25? See, earlier it was like, you've got this much acid, you've got this much base, what's the pH going to be? Now we're asking the opposite question, right? Now we're asking, hey, I want the pH to be a certain amount, and I need to know what the ratio should be. I'm still going to use that equation. It's pretty short, but as long as X is small, or and hopefully you recognize what ratio means. I'm asking for what's the number inside there. I'm not actually looking for A minus, nor am I looking for HA. I'm looking for the ratio of those two. Because the ratio of those two is what becomes the pH. Remember all those curves on that one diagram where they all overlap in the same place except one's kind of farther than the other? Is that kind of an idea? So let's see here. What pH am I trying to get to? 4.25. What's the pKa of formic acid? 3.74 plus the log of that ratio that I'm trying to find. So here I'm trying to solve for that ratio. And I just arbitrarily use the letter R. I could easily let X and X. That's what I do. So let's see. How do I do this? These fingers punching on calculator, so yes, you already know how to do it. I'm going to subtract 3.75 from both sides. So that's going to give me 0.51 on the left is equal to the log of whatever that ratio is. How do I get that log off of there? Yeah. So I got to do 10 to the log of R is equal to 10 to the 0.51, which 10 to the log, that cancels each other out, and so R is 10 to the 0.51. Let's turn that into a sweet number. Did you do that? How much? 3.24? So what that tells me is I need the ratio of A minus to HA to be 3.2, and the nice simple thing would be to 1. So let's make the A minus 0.32 molar, and let's make the HA 0.01. really doesn't matter as long as that ratio is 3.2 to 1. So as long as I have 3 times as much base as the acid component, I'll get the buffer that I want. Now I'm going to go for higher concentration if I can. So maybe I'll go for 0.6 to 0.2, a little bit higher ratio or capacity. But for the moment, my point is to figure out what that ratio is. And that ratio is 3.24 to 1. Ratio needs to be 3.24 to 1. Of course, how do I get that? Anions, sodium salt, potassium salt, that's option there. Questions on it? This one I'll leave to you to do. What's the ratio of sodium benzoate to benzoic acid? To get myself a buffer worth 3.75, knowing that the pK of benzoic acid is 4.19. So again, it's the same kind of calculation. I think you guys can do that. So here's what we've said so far, and this is where we'll finish for today. Buffering capacity, just how much acid or base can you add before you lose that resistance, at least a significant amount of that resistance. So we get more capacity with more concentration. That's what we said. We get more capacity the closer to 1-to-1 we can be. But remember that 1-to-1 forces us to a particular pH, right? Whatever the pKa, a 1-to-1 ratio, is going to give us what the pH is. But if we want to be slightly one way or the other, then we can modify that ratio, figure the pH we want. That's what we just got to notice. But the closer to that 1-to-1, the better. These last two lines, I don't want to say a whole lot about them, but just there's some tweaking that you can do. Okay. So if you've got a choice of two of them, one's a little bit above your target, one's a little bit below your target. If you know the conditions are more likely going to be added acid or more likely to be added base, you can tweak your choices to one side or the other. Because as soon as you get off of that 1-to-1 ratio, you're going to be a little bit better buffering against one than the other one, depending on what you have more of. If you have more of the base component, you're going to be better able to buffer against acid. If you have more of the acid component, you're going to be better able to buffer against base. That's what happens. All right. Next thing we're going to talk about on Friday when we get here is titration. So we're going to go back to that stoichiometry, and we're going to go through a series of calculations. Those graphs that were pre-drawn for you, we're going to learn how to draw those ourselves by hand. How to calculate and what here, what there, what there, what then, okay, that kind of thing. So that's where we're going on Friday. All right, thanks for coming.